Okay, so for number one here, our percents, 45%, of course, is 45 over 100. 60 go on top or bottom?
Bottom.
Bottom. Oops. 16, not 16. We cross, multiply, and divide, and we get 27. Number two, we're missing the percent, so it's blank over 100. We've got the 32 and 80. Which one goes on top? 32 over 80. Cross, multiply, and divide, we get 40. That is 40%. Number three, 70%, so that's 70 over 100. 56 go on top or bottom? Top. We cross, multiply, and divide. 100 times 56 divided by 70. We get 80. 70% of 80 is 56. And finally, number four, 115% is 115 over 100. Does the 80 go on top or bottom? On bottom. So now we cross, multiply, and divide. 115 times 80 divided by 100 is 92. Yes, that would work. In fact, this one would have been the same way. You could have just done 60 times 0.45. Yep, and here, yes, 80 times 1.15 would have worked. When it's that piece, that portion, which would be the top number in that second ratio, you can always use that rate method by multiplying. One of the biggest applications in machining for that is if you're using a waste factor. You know, if you have a 10% waste factor or 5% waste factor or whatever, you're going to multiply by 1.10 or 1.05. Okay. Well, we talked a little bit about similar figures, where one is an enlargement or reduction of the other. To know that two triangles, we're going to stick with mostly triangles at the beginning here. To know that two triangles are similar, all you need to know is that two sets of angles are equal. So this angle here that I marked and this angle here that I marked are the same because I marked them both with a single arc. I'm going to mark this one with a double arc and this one with a double arc. So those two angles are the same. So we know that those are similar. In other words, the big one is just an enlargement of the small one, or you can think of the small one a reduction of the big one, whichever way you want to look at it. So let's say that this here is 6 inches, and this here is 20 inches. I'm going to call that one X for now. This one's going to be 15 inches. This one's going to be Y inches. This one's going to be 40 inches. First thing we have to do is figure out which sides correspond. So starting over here, the 40-inch side. In the larger triangle, which side corresponds to that in the smaller triangle? The X does. They're both between the angle marked with the single arc and the unmarked angle. So they're both between the same two angles, they have to correspond. What corresponds to the 15 in the other triangle? The 6. Very good. They're both between the unmarked angle and the one marked with 2 arcs. And then finally, what corresponds to the Y? Better be the 20. It's the only one left. They're both also between the angle with the single arc and the angle with the double arc. Now, to work with similar figures, one of the first things we need to do is find a side where we know the length of both corresponding sides for both figures. That's the 15 and 6. So I'm going to do 15 over 6 is my ratio of sides. That is a constant ratio between two similar figures. I'll just call it the ratio of length. So all lengths from one figure to the other are increased or reduced by that same ratio. So now let's find x. Is x going to go on top or bottom? Why on bottom? If it is from the same figure as the 6. And remember, we've got to have relationships in both directions. A relationship going in this direction is because those are corresponding sides. The relationship we're going in this direction is they're from the same figure. So the piece that goes here has to be from the same figure as the 15, and it has to be the corresponding side to the x. So the 15 is over here, and yes, you're right, the corresponding side is the 40. So we will cross, multiply, and divide. 6 times 40 divided by 15 gives us 16, I believe. Perfect. How do we find y? Okay, we start out with that same ratio of lengths. Y is going to go on top because it's from the same figure as the 15. What goes below the y? The corresponding side is the 20. So we shall cross multiply and divide. 15 times 20 divided by 6 is, what is that, 50? So 50 inches. Corresponding figures or similar figures do not have to be just two-dimensional. I can take a three-dimensional figure and enlarge it and still get similar ratios of sides. So let's assume that these are similar figures. So let's say that this is 20 feet. This is 8 feet. Let's say this is 20 feet. We're going to call this X. I want to find the height of the bigger pyramid. What sides correspond here? The 20 feet and 8 feet are both the side of the base. And of course, we do have the X corresponding to the 20. The heights correspond. So we're going to start out with the 20 over 8 or 8 over 20. Doesn't matter which way we do it. On the other side, though, the X has to go on top because it goes with the 20. Same figure as the 20. So the other 20, the height of the other one goes below it. So we shall cross multiply and divide, and we get 50. So that height is 50 feet. Simple enough. So whether we're two-dimensional or three-dimensional, similar figures are going to have a common ratio of length. Now, there are other aspects of figures other than just lengths that we might be interested in. For example, Let's say this figure is 2 inches by 5 inches. And we're going to blow it up. This is now 6 inches. What's this dimension up here going to have to be? Yeah, 2 became 6, so 5 becomes x. We cross multiply and divide. 6 times 5 divided by 2 is going to be 15 inches. So what we just did there was a ratio of lengths. It was 2 to 6. Or if I reduce it, 1 to 3. What's the area of this figure up here? 10 inches squared. 2 times 5, 2 inches times 5 inches is 10 square inches. What's the area of this figure? Yeah, 90 inches square, 90 square inches. If I compare those, get a ratio of areas of 10 to 90, which reduces to 1 to 9. You'll notice ratio of lengths, ratio of areas is not the same. Let's look at another example and see if we can come up with a pattern here. So let's say that that is 5 inches and 12 inches. We blow this up so that this is 10 inches and 24 inches. What is the ratio of lengths? Well, I either do 5 to 10 or I can do 12 to 24, right? Yeah, either way, you're exactly right. It reduces either 1 to 2 or 2 to 1. So 1 to 2 or 2 to 1 ratio, depending on how we look at it. What's the area of this? 60 inches squared. The area of this? 240 inches squared, 240 square inches. My ratio of areas is 60 to 240, which reduces to 1 to 4. Do you see a relationship between these two numbers and these two numbers? What's 1/3 squared? 1 squared would be 1. What's 3 squared? What's 1/2 squared? Yeah, 1 squared is 1, 2 squared is 4. Let's see if that holds true. Hang on. Don't get all wound up and go running off. So our ratio of lengths here is what? 3 to 5, right? 3 becomes 5, 9 becomes 15. You're going the wrong, you're going within a figure. The area of this one is 27 square inches. Area of this one, 75. So the ratio of areas, 27 over 75. Both of those, by the way, can be divided by 3. Give you 9/25. Does that hold true? What is 3/5 squared? Well, 3 squared is 9, 5 squared is 25. Yes, it does. Well, in standard simple figures like I've drawn here, that really isn't a useful piece of knowledge. You can find the area of a rectangle pretty easy. You don't really need to worry about ratios of areas. But I might have a weird shape like that. I almost made those look the same. And let's say this is 5 inches and reduce it to 3 inches. And we say the area of this is 750 square inches. And I want to know the area of that. We can actually find that area. If I know that this is a reduction of this bigger one, I can do the ratio of lengths. Is 5:3, which means my ratio of areas we found by squaring that. 5 squared is 25, 3 squared is 9. My ratio of areas is 25:9. I have the 750 square inches. Where does that go? Yeah, it's from the same figure as the 5, so it goes on top. So we have 9 times 750 divided by 25, which is what, 270, I believe? Square inches. So that figure would be 270 square inches. When there's a figure like that where calculating the area directly is really tough to do, we can find the area after an enlargement or reduction by using those ratios. And area and surface area will work the same way because they're still just areas. So if I have an object it does kind of, doesn't it? Yeah, I know I'm cheating. There's only so far my artistic ability takes me, and then I've got to use technology to cheat. I could possibly make 2 of them that look sort of alike, but trying to make 4 of them that were anywhere close would not be beyond my artistic abilities. So let's say that this shape here, this height right there, is 12 inches. On this one here, it's increased to 20 inches. Let's say the surface area on this small one is 600 square inches. I want to find the surface area on the large one. Well, it's still an area. So I'm going to start out with my ratio of lengths, which will be what? 12 to 20. Now, I'm going to make life a little bit easier on myself by reducing those. 12 divided by 4 is 3. 20 divided by 4 is 5. So it's 3 to 5. Now, surface area is just an area. So I'm going to get my ratio of areas by doing what to my ratio of lengths? Squaring it. That's going to give me 9 over 25. 3 squared is 9. 5 squared is 25. And I know the 600, which goes with the 12, so it goes on top. So we cross multiply and divide. So 25 times 600 is what, 1,500? Divided by 9 is 1,555.55? Did I do that right? 50. Okay. Should be 16.67. It's actually 15,000, not 1,500. So 1,666.67 inches squared is that surface area. That's where we're going next. I can see it. So now we're ready to proceed to that, though. You were just too far ahead of your time to fit in at the moment. Okay, so let's say that this is 2 inches on a side. And we blow it up. So that it is now, let's go 6 inches on a side. Our ratio of lengths is going to be 2 to 6, which we will reduce 1 to 3. You got her. Volume. Well, 2 times 2 times 2 is 8 inches cubed. And here, this volume, 6 times 6 times 6 is 216. So our ratio of volumes is 8 to 216. Now this does divide, it does reduce. Both of those divide by 8, which gives me a 1 to, was it 32? No, 27, there we go. Now you asked, does that relationship hold if we do what here? Cube it, what's 1 cubed? 1, what's 3 cubed? 27. So yes, it does hold. So then, back up to this pretty little problem. If I tell you that the volume of this smaller figure is, oh, let's see here. Let's say that that is 540 inches cubed. Let's find the volume of this bigger figure. Well, we already have our ratio of lengths is 3 to 5. The 12 to 20, we reduced it to 3 to 5. To get our ratio of volumes, we need to do what? Cube it. What is 3 cubed? 27. 2 times 3 times 3. 5 cubed? 125. Very good. Over here, where does the 540 go? On the top. That is from the smaller figure. So then, cross multiply and divide. 125 times 540 divided by 27. Is that 2,500? Cubic inches of volume. What do you think? Still better than a sharp stick in the eye? So let's have some fun. This lack of trust thing is just, it's starting to bother me. Railroad iron. Wow, a bunch of critics. Yeah, make up a quiz for tomorrow morning. Robin wasn't the only one heckling now. There, how's that? Better? To take this outside. I have to go home and cry myself to sleep again tonight. There you go. Yeah, don't picture that. Actually, you know what? That's not, since you guys are heckling, let's make this more difficult on you. That's going to be X inches. This is going to be 20 inches. The surface area here, get back here. It's going to be 1,250 inches squared. We're trying to find the surface area here. The volume here is 1,200 cubic inches. Trying to find the volume there. I suppose I gotta give you at least one more piece of information, don't you? Okay, so, wow, that wasn't very nice. We'll call that 200 square inches. So I gave you the surface area for both. You need to find this dimension and this missing volume. I'll give you a couple minutes to try that. Okay, let's see what progress you've made. We are starting out here with the ratio of areas, which is, in this case, 200 over 1,250. Now, I don't have to include the inches squared because that's just going to cancel out. Now, these can both be reduced. Both of these can be divided by 50, which gives us 4 over 25, correct? You may have divided both by 10 first and then by 5, but either way you'll get there. Well, that's the ratio of areas. If I want to go backwards to the ratio of length, how do I get there from the ratio of areas? Square root. Very good. What's the square root of 4? 2. What's the square root of 25? 5. So my ratio of lengths is 2 to 5. So I have the 20 inches. I will cross multiply and divide to get that this is 8. So 8 inches is that length. You okay there? To get my ratio of volumes, I'll take that 2/5 and cube it. 2 cubed is 8, and 5 cubed is 125. My volume of 1200 goes on the top. We shall cross multiply and divide to give ourselves perfect 18,750 inches cubed is the volume. Now, oftentimes the tricky part when dealing with these ratios is deciding whether it's a ratio of volumes or a ratio of areas. For example, so we have an exhaust pipe. We have an 8-inch diameter exhaust pipe. Can expel 120 gallons per minute. How much could a 10-inch pipe expel? Now, this one's confusing because this number right here is a volume. Well, it's a rate, but it's assuming volume, right? You see gallons, you think volume. But are we changing the volume of the pipe? We went from 8-inch diameter to 10-inch diameter. What we changed was the cross-sectional area of the pipe. Bless you. The area of the pipe increased, not the volume of it. For this problem to have changed volume, remember we have this pipe. We'd have to also change the flow rate of the fluid or whatever is flowing out of that pipe. Does that make sense? As long as that flow rate stays the same, changing the diameter just changes the area, the cross-sectional area. So this really is an area problem. So our ratio of lengths is 8 to 10, which of course reduces to 4 to 5. We are going to square that to get a ratio of areas of 16 to 25. And we'll use that with our 120 gallons per minute. 120 times 25 divided by 16 is 187.5. So that would go up to 187.5 gallons per minute. So that's the tricky part with these problems, is figuring out what is, is it an area or is it a volume? I'm going to hand you a worksheet. On this worksheet, problems 1 through 6 are just ratios of lengths, similar figures. take a look at some of those. Make sure you do some of those. But the ones I really want you to focus in on are 7 through 16, which are the word problems. Preemptive.